Going to do a version of example 9.4 about dropping your phone and calculating the impulse and the average force that the phone experienced. So the idea is that you take a phone, say the iPhone 12, and you drop it by mistake just a meter above the ground. And it hits the ground and bounces back up. And so the question is, what kind of force does it experience on average? What's the change in momentum? All of those kinds of things. And this won't answer whether it cracks or not, because that, of course, depends on the materials and the angle and all of that. Hopefully you have it in a good case, so this is not an issue. But what I want to point out is when we have this falling, first of all, we can find out what its speed is right before it hits the ground. We can just use energy conservation for that. We can say its initial, it's all potential energy, and then right before it hits the ground, we're going to find out its speed right before hitting. So this is, I should say, right before it hits. And so as we look at this, we can say energy initial, energy before hit. And so U is equal to mgh. K is equal to 0 if it drops from like slipping out of your hands. You didn't throw it down, for example. And the potential energy, we're going to call that the Y equals 0. And the kinetic energy gives us then our final speed before hit. And so if we solve these, we have mgh is equal to 1/2 mv squared. We got plus a 0, and the mass is canceled. V is equal to the square root of 2gh. And when I put in 1 meter for that, I get a speed of about 4.5 meters per second. Okay. So we're going to kind of look at that hitting the floor. So here's the floor, and we're going to say this comes in at a speed of 4.5 meters per second. It's a nice elastic collision. It bounces back up, at least initially before it falls and clatters on the ground, at 4.5 meters per second. So what I want to now know is the change in momentum, which would give me then the impulse, and that's going to be equal to basically our average force, because we don't know how it's going to change over the time of the collision. Okay, so our change in momentum, this is a little tricky. Some people will say, well, it must be 0 because the speed going in is 4.5 and the speed going out is 4.5. But you have to be careful because momentum is a vector, and momentum initial is m, I'm going to have to know the mass of the iPhone, times the speed, 4.5 meters per second, in the minus j hat direction. That's the initial. And then the final here, after the collision, is the mass. And I guess I should look that up. I've got about 0.16 kilograms. 0.16 kilograms. So that's what's there. 0.16 kilograms. Again, times 4.5 meters per second. And this is in the plus j hat direction. So if we look at the change in momentum, notice that in general, this is going to be the mass times velocity for the final. So that is, I don't know what the number is. I didn't actually calculate that number. I'll just rewrite it. 0.16 kilograms times 4.5 meters per second in the j hat direction minus this 0.16 kilograms times 4.5 meters per second in the minus j hat direction. I've got two minus signs, so that gives me a plus. So my change in momentum is equal to 2 of these kilograms. I'm going to put all the units at the end here. This times this, and this is kilograms meters per second. Okay, so that's my change in momentum there. After I put this in my calculator, I get it to be 1.4 kilogram meters per second in the j hat direction. So that's my impulse, that's my change in momentum, and that's going to equal the average force over the time of the collision. And to find the time of the collision, we tend to estimate it by saying, well, how long would it take the object to travel the distance that the height that the object is. That's just a way of sort of estimating that. So if we say the height is 0.15 meters, 150 or so millimeters, then we can say the speed right at the bottom, speed is equal to approximately, this is our equation, the height over this delta t, which is the collision time. This isn't really it just tells you whether it's seconds, tenths of seconds, millions of seconds, just to get a feel for that. So we can get a delta t is equal to h over a v, or 0.15 meters over 4.5 meters per second, and that gives me about 0.03 seconds, which would be about 30 milliseconds. A little long for this kind of a collision. Your phone might survive that. And if I put all these pieces in my main equation, delta p is equal to v average delta t. Of course, the force it feels is up because this is in the plus j direction. And I can put in my delta t of 0.03 seconds. I can put in my 1.44 kilogram meters per second in the j hat direction. And my average force then is about 48 newtons in the j hat direction, because it's kilograms meters per second squared, which is a newton. That doesn't seem too bad, but if you compare it to its own weight, right, the weight of the iPhone, it's pretty, it's not very massive, right, because you're carrying around. It's not too heavy. The weight is m times g, and when I look up, our m was the 0.16, 160 grams times 9.8 meters per second squared, just for comparison. Then I get this is about 1.6, of course, newtons. So this is many, many times. It's 30 times its own weight. So that's a pretty substantial hit. And again, I think this has overestimated the time of collision when this happens, which is, of course, why we damage our phones if we drop them. So get a good case or hold on to your phones.